let's say I have a sine wave which can be expressed as 70, let's say 170 volts times the sine of 377t. Let's draw us a picture of that sine wave. That sine wave has a peak amplitude of 170 volts. And we need to know it has an angular velocity of 377 radians per second. So if I do a little bit of a calculation, this is a 60 hertz sine wave, but I can find out what that frequency is just by looking at this number here, because I know that omega is equal to 2 pi times the frequency. We just talked about that. If omega is 2 pi times the frequency, if I divide 377 by 2 pi, I should end up with the frequency. And if I do that, divide 377 by 6.28, I end up with approximately 60 hertz, or 60 cycles per second. If I do the reciprocal of that, I would get 16.66 milliseconds. Okay? So the time between the beginning of one cycle and the beginning of the next is 16.6. We'll go ahead and round it off. 16.67 milliseconds. So I can pull the frequency right out of that 377 number, that omega number, just like that. So now then, let's say that I wanted to know what is the value of this sine wave at, say, let's see, 16 divided by 4 is about 4. Let's say about 4.2, let's choose about 4.2 seconds, or milliseconds, excuse me, into the sine wave. So I would put right here, I would plug in 4.2 milliseconds, multiply that times 377, make sure my calculator is in the radians mode. Got to get my calculator in the right mode here. Okay, now I'm in the radians mode. I'm going to take 4.2 milliseconds, 4.2 times 10 to the negative third, and I am going to multiply that times 377. That ends up with 1.58. I'm going to take the sine of that, which is, hey, all that thing comes to is 1. So 1 times 170 is 170. So that's showing me exactly that I am at the peak voltage at 4.2 milliseconds. So I hope that helps you relate to how that function is used to find the instantaneous value at some time t. Of course, if you needed to know the time at which the voltage is a certain value, you could put that value in here and solve the function for t. I know y'all are all algebra experts, so you could do that with no problem. All right, here we are, part 3 of this AC math theory. I want to impress on what I've got a circuit up here, an RLC series circuit. And I want to tell you that all the things that you did with DC, all the logic, all the thinking, what's in series, what's in parallel, all that business still stays the same. The calculations in AC are the same as they are in DC, except that we must carry the angles. Must always carry the angles. Now, if you drop an angle, you're going to get an incorrect answer. Okay, the first thing we're going to do with this circuit, I've got to take a look at it here. A 50 ohm volt RMS source, and unless you're told otherwise, you assume that it's RMS. We've got a resistance of 100 ohms, an X sub C of 250 ohms. And an X sub L of 75 ohms. First thing we're going to do is write the impedance equation in rectangular form. Now remember, we said we use positive J for X sub L, negative J for X sub C. So we have Z total is equal to R plus JX sub L minus JX sub C. So when we fill in those, we have 100 ohms plus J 75 ohms minus J 250 ohms. Now we can simplify that further right off the bat, because we know that X sub L and X sub C are pointing in exactly opposite directions, and when it comes to adding vectors, if they're pointing in exactly opposite directions, we just take the difference and go with the largest one. So we've got 250 here, and we've got 75 here, so we're going to end up with negative 175. The resultant of that is negative 175. So you can do that, it's just a simple subtraction. So we've got X sub L minus X sub C, so we'll end up with 100 minus J 175, and that's our resulting equation. Anytime you have X sub C and X sub L in a series circuit in the same direction, you take the impedances and boil it down to one or the other, or they may get rid of each other altogether if they're exactly the same value. Okay, so this is our impedance equation in rectangular form. Let's convert that to polar. What do? I take, to get the magnitude, I take the square root of the sum of the squares. So 100 squared plus a negative 175 squared, and that'll turn out to be a positive number. And that'll give me, and then I take the square root of that sum, Pythagoras theorem, and that gives me a 201.6, and then I find the angle by taking the ratio of the J value to the R value, and then in the inverse tangent of that. Anyway, I get negative 60.26 degrees. So what I'm looking at is a vector of minus 175 here, minus J 175, and a resistance vector of 100. So if I make that one that long, I need to make this one about this long. This is set 100, and this down here is 175. All right, so now then, that's my phasor, or my vector, that represents the impedance in polar form. That's my 60 degree, negative 60 degree angle right there. All right, now then, let's find the current in the circuit. Current is always V divided by, in this case, Z, right? Resistance, opposition to current. Okay, V divided by Z. So now that I've got this thing in polar form, remember I said I multiply and divide in polar form. I'm going to divide 50 volts at an angle of 0 degrees divided by 201.6 at an angle of negative 60.26 degrees. I know this looks strange, but it's going to work out so easily. So I is equal, we simply take the 50 and divide by 201.6 and we get 248 milliamps. And now what we're going to do is we're going to subtract a negative 60 degrees from 0. When you subtract negative 60 from 0, you get a positive 60. If we had a number up here, we would actually have to do a computation. So there's my current. My current is a 248 milliamps of current are flowing in this circuit. Alternating, of course, one way and then the other. And it has a phase shift with respect to the voltage source of 60.26 degrees. That's what the current does. All right. If I go back now and I take, and I want you to do this in accordance with the worksheet because you can do these calculations. I want you to go back and multiply this current with its angle times R at 0 degrees. And I've illustrated this exactly in the handout. And see what you get. I want you to do the same thing times x sub c, and x sub c though will be at negative 90 degrees. Be sure you put that angle in there. And x sub l will be positive 90 degrees. So when you combine those things, be sure you add those angles. It's illustrated precisely the way I want you to do it in the book. And I did it one time without the angles, and I did it one time with the angles. And so when I did it with the angles, I converted the values back to rectangular form and added the R component and the J components, and that came out exactly right. And I also drew you a vector diagram. The other thing I need to talk to you about on this briefly is the difference between true and apparent power. Apparent power is the power that appears to be being dissipated by the circuit. And as we discussed right in the beginning, x sub l and x sub c do not dissipate any power because their opposition to current is not due to friction. All right, the last time that we got together, we were just about to talk about the power in AC circuits. And just as an example here, this would be the equivalent circuit of the circuit we just got through working. Remember, we had more capacitive reactance than we had inductive reactance, so it boiled down to an RC circuit. So we had a, let's see, we had a total impedance of 201.6 at an angle of negative 60.26 degrees. That was the total impedance that the source sees looking into that circuit. Now again, what I had said was that when we calculated current, and the current was, let's see what the current was. Current was 240 I total, which is the current throughout, because it's a series circuit, was equal to 248 milliamps at an angle of 60.26 degrees. Same angle as the impedance, except positive instead of negative. All right, now then, the voltage we had applied to this circuit, the V source, was 50 volts at an angle of 0 degrees. We didn't have any phase angle associated with our source voltage. Now then, we were talking about power, and what I had said in our previous session was that the power that appears to be dissipated by the circuit, or the apparent power, is not the same as the real true power of the circuit. And again, the reason for that is because the only component in this circuit that dissipates real power is, or true power is another term for it, is the resistor. The capacitor's opposition to current is due to stored energy, and therefore it does not dissipate any power. So we have two things here we need to learn about. One is a thing called the power factor. And the power factor of an AC circuit is equal to the cosine of theta, where theta is the phase angle of the circuit. In this case, it would be the phase angle of 60.26 degrees. Okay. Now then, if we take a look at our vector diagram for this circuit, if you will recall, we would have had our X sub C in the negative direction here, and we have our resistance in the 0 degree direction, and we have this impedance vector here where this is theta and this is about 60 degrees. Okay? Negative 60 degrees, excuse me. Approximately negative 60 degrees, negative 0.26 to be exact. So what we are looking at here, the cosine of the phase angle ends up being the length of that side of my triangle. And see, that is the resistance component of the impedance. So it makes sense that the power factor represents the proportion of apparent power that is due to resistance. So if we knew our apparent power, which we can just do by saying I times V, which would be just simply the 50 volts multiplied times the 248 milliamps, the apparent power for that circuit would be 12.4 watts. Now this is worked out in your handout, so you shouldn't have any trouble seeing how I did that. Just simply multiplied the current times the voltage. That's apparent power. Now then, if I take the cosine of theta and multiply it times the apparent, that will give me true power. Or another way to say that is the real power, or the resistive power. Maybe you can associate real with R for resistance and come up with real. All right. The cosine of theta in this case turns out to be approximately 4.9, or 0.49, excuse me, 0.496. So 0.496, which is the cosine of 60.26 degrees, and the apparent power of 12.4 watts gives me a true power of 6.15 watts. Now then, I would get exactly the same number if I took my current and multiplied it times my resistance. That would give me that same number. So you check that out and see that that is true. All right, this is part 4 of the AC math worksheet, and in this section we are going to go through an example of how to find all the currents and voltages with respect to a parallel, actually it is series parallel RLC circuit. But what we have here is we have a circuit which has two impedances, Z1 and Z2, in parallel with each other. I've outlined them in a green dotted line. R1 and X sub C make up one series combination of R and C. And an RL circuit, Z2, is in parallel with that. And the objective here is to find, first of all, total impedance. And then we would like to find the current. We'd like to know the power factor. And I've gone through the detail of finding the voltage drops across each of the components. And you should be expected to be able to do this. Maybe not until you have actually done some study with just the simple series circuits first, the RL and RC series circuits. But at some point pretty soon, particularly in AC2, you'll be expected to do this, and we might even add another series impedance up here that would be in series with a parallel combination of Z1 and Z2. So this is the next step. All right, if I'm looking for Z total in this particular circuit, the first thing I'm going to do is write out the formula. Do you remember back in the beginning of this tape, I told you that you would carry through the processes just like you did in DC for series and parallel and series parallel combination circuits. The only difference being that you had to carry the angles along. So if we had a circuit like this that was two resistors in parallel, we would say 1 over R total is equal to 1 over R1 plus 1 over R2. So we're going to do the exact same thing in our circuit here. We're going to say 1 over Z total is equal to 1 over Z1 plus 1 over Z2. Now, Z1 turns out to be 500 minus J180. I've got the values here on the board. Z2 turns out to be 250 ohms plus J200. So we'll go ahead and substitute those numbers here. Now then, we are going to take the reciprocal of those numbers, so that implies division. And multiplication and division always takes place in what form? Polar form. So we'll have to convert those into polar form. I've done that. So 1 over Z total now will be represented as 1 over 500. 1 over ZT is equal to 1 over 531.4 at an angle of negative 19.8 degrees. Plus 1 over the reciprocal of 250, which is 320. Oh no, that's not the reciprocal of 250. I'm sorry, that is just the magnitude of the polar conversion. 320 at an angle of 38.66 degrees. Now we are prepared to take the reciprocal. The reciprocal of 531.4 is 188 times 1.88 times 10 to the negative third. Now, the reciprocal of the angle, remember the angle on top, if it's not indicated, is going to be 0. So 0 minus a minus 19 will be a positive 19. So this turns out to be 19.8 degrees. And then we need to add that to the reciprocal of 320, which is 3.13 times 10 to the negative third. And this angle will be negative because 0 minus 38.66 will be a negative 38.66. All right, now then, I've taken my reciprocals. Now what I need to do is I need to add these two things together. Now you don't have to memorize the sequence of events. Once you write this down and start working the problem, the mathematics will lead you through the necessary steps. All right, in order to add these two numbers, they're in polar form, what must I do? My best idea for you would be to convert them to rectangular form. So I would say 1 over z total is equal to, I have my conversions here, 1.77 times 10 to the negative third plus j 636.8 times 10 to the negative 6 plus the second one is 2.44 times 10 to the minus third minus j 1.96 times 10 to the negative third. And now I simply come along here and I've got, that's my rectangular forms. And remember, when we add and subtract in rectangular form, we combine r's and j's separately. So this r with this r, this j with this j over here. So when I carry that out, I get 1 over z total is equal to 4.21 times 10 to the negative third. And which is bigger, the plus j or the minus j value? The plus j value is bigger, so it's going to, the minus j value is bigger, so it's going to be a negative, whatever the difference is of 1.32 times 10 to the negative third. I need a j there, so I indicate it's a j component. All right, now then, in order to carry this out and find z total, the next thing I have to do is take the reciprocal of both sides. So 1 over z total, 1 over z total is simply now my z total. I'm finally getting to it, aren't I? So I would have the reciprocal of this combination here. So that would be 1 over 4.21 times 10 to the negative third minus j 1.32 times 10 to the minus third. And now I have to convert that into polar form because I'm going to have to divide again. So 1 over 4.41 at an angle of negative 17.45 degrees. And now I simply take the reciprocal of that, and I have z total in polar form. The reciprocal of that is 226 at an angle of 17.45 degrees. And again, the only thing I had to do was take the reciprocal of 4.41 times 10 to the negative third, take the reciprocal of that, and go change the sign of the angle, because the angle on top is a 0. Now then, that's the form that we need the total impedance in. So now I'm going to come back up here and write that expression out here. Z total in polar form is 226 at an angle of 17.45 17.45 degrees. That way I can use the rest of the board to finish out the other calculations. All right, continuing on now, we found Z total was 226 at an angle of 17.45 degrees. The next obvious thing for me to find would be the total current flowing in the circuit. So to do that, I would simply divide the source applied voltage by Z total. If you look back at the circuit in the worksheet, it tells you that source voltage is 120 volts at an angle of 0 degrees. And our Z total, now look, this is just Ohm's law, V divided by Z. Potential applied to the circuit divided by the opposition to current. That's going to give me the current. I is V divided by Z, just like I is V divided by R. Okay, so 120 at an angle of 0 degrees divided by 226 at an angle of 17.45 degrees. 120 divided by 226 is 529.6 times 10 to the minus third. We'll just use milli at an angle of negative 17.45 degrees. Why is that a negative angle? Well, I had to subtract angles. 0 minus 17 is negative 17. So now, that's I total. That would be the current combining at this node here, coming in from both of those branches. And so what I'm talking about is this current flowing back into the source after that node. I total. Now, I need to find the voltage drops across each one of these components here, so I need to know the branch currents. IZ1. The voltage across the parallel impedance branches are the same because they're in parallel. So that would be IZ1 would be 120 volts at an angle of 0 divided by V divided by Z1. Okay? And Z1 was 531.4 at an angle of negative 19.8 degrees. So carrying that out, 120 divided by 531.4 and bringing the angle back up, making it positive, gives us an IZ1 of 225 milliamps at an angle of 19.8 degrees. Now then, IZ2 is worked out in a similar fashion. IZ2 is worked out in a similar way. We take the 120 volts at an angle of 0 degrees and divide by Z2. And Z2 is 320 at an angle of 38.66 degrees. And that turns out to be 375 milliamps at an angle of minus 38.66 degrees. All right, now then, I have done the rest of the math for you in the handout, and so you can look at that to do the rest of it. But in order to find V across R1, for example, you would take IZ1 times R1. And IZ1, be sure you use the whole thing, include the angle. And R has an angle, of course, of 0 degrees. So you should be able to see exactly how I did that in the handout. And once you find those voltages, in order to check yourself, you can go back and add them up and see that everything comes out correctly. Remember, always carry the angles. And if you're not given an angle, consider it to be 0 degrees. All right. Part 5 of the AC Math handout and the AC Math theory is on logarithms. And I know that sounds like a very exciting subject to you, but may not be exciting, but it's one that's necessary for you to have some background in. So we're going to talk about that just a little bit. The first thing I want to impress upon you is what a logarithm is. A logarithm is an exponent. And it's just exactly that simple. A logarithm is an exponent. Everybody knows what an exponent is. If you've got some number and you raise it to a power, x in this particular case, then the x is the exponent. All right, the x is an exponent. Well, there are two different ways to express the relationship between an exponent and the number that we're raising to that power. The first would be something like this. 10 raised to the x power is equal to y. Let's do an example. 10 raised to the second power is equal to 100. I think everybody knows that without even having to think about it. 10 times 10 is 100. Okay, another way to express that exact same relationship is to say the logarithm, and we'll reduce it to a shortened version, just say the log base 10. And that's an important little subscript there, the log base 10. That tells you the number that you're raising to a power. Log base 10 of y is equal to x. Now what did I tell you before? I told you the logarithm was an exponent, didn't I? The logarithm is an exponent. And so what have we done here? We have said the logarithm of y to the base 10 is x, and x was, let's mark that in red, x was your exponent, wasn't it? And so you can see how that works out. Now the other way to write that out in something that with which you are familiar would be to say the logarithm of 100 base 10 is equal to 2. So you can see that we've got the 2 here is the exponent, and we're representing that in that relationship between those two numbers, or those three numbers, in a different fashion, just writing it out in logarithm form. Now then, this does some important things for you. In electronics, we can use logarithms to deal with calculations that involve sound, power levels, and frequency response. And there are two forms that we're going to deal with, two log bases that we're going to deal with. One is the base 10. That's what this is called, the base. The other thing is we could have a log base E of some number. I probably shouldn't use the term x there, since I just used x for the exponent. Log base E of y. Well, everybody knows what 10 is, but nobody knows what E is. E is it's the base of the natural log system, but it's also a number that occurs in nature. If you had a dish, I call them a Petri dish, I guess, from old science courses I had, and you seed that thing with some bacteria, and then you monitor the growth of that bacteria over a period of time, you would find that the growth of the bacteria colony increases exponentially according to a particular curve. And if you also study the level of salomes as your ear responds to them, it responds exponentially by the same curve. Isn't that interesting? So that curve is based on raising E to some power, okay? Raising E to some power. Therefore, we have what we call the natural log system. LOG base E of Y. And so that we don't have to write LOG base E, we write LN for natural log. And anytime you see LN, it's on your calculator, and sometimes you replace it, it's mistaken for IN, it's really LN. And you'll see that LN and E to the X are often on the same key. They should be on the same key on your calculator because they're just exactly opposite functions of each other. So that's where that term natural logarithm comes from. There's an equation that you will deal with pretty soon, talking about the charge on a capacitor, the voltage across a capacitor at any time t is equal to the voltage applied, or the maximum voltage it can be charged to, times 1 minus E to the minus t over the time constant of the circuit. Now don't worry about what all that means right now. I'm just showing you there's an application for knowing about E. E is in your calculator. If you say E to the 1, you put 1 in your calculator and you say E, hit the E to the X button, your answer up on your screen should be approximately 278.128, I believe it is. Let me go look that up right quick so we'll be sure that we get that right. All right, I just did exactly what I told you to do. I put 1 in my calculator and hit my E to the X button, and it comes up as 2.71828. And if you show all your decimal places, you'll see that that's a non-repeating, non-terminating decimal. It'll keep going 1828, 1828, 1828. For practical calculations, we would just stop right about here. 2.718 would be plenty of round off, plenty of digits to get the accuracy that we're needing. In fact, you don't even have to take the number out of your calculator, and that gives you the most accurate use of the number. All right. Now we know what a natural logarithm, and we know what is, and we know what E stands for. Here's some rules that will be helpful to you when dealing with logarithms. If you have the log, I'm just going to put a B here for the base because these apply to natural logs as well as base 10 logs. If you want to take the logarithm of x and you need to add it to the logarithm of y, it's an equivalent thing to say that is exactly the same as the log of x times y. So in other words, the logarithm of x plus the logarithm of y is the same as the logarithm of x times y. Or go ahead and do the product of x and y and then take the logarithm. That'll give you the same answer. Okay, the other one is log x minus log y is equal to the logarithm of x divided by y. So again, you can get the same answer both ways. And here, this one is pretty useful in doing algebraic solutions. The logarithm of x raised to the nth power is equal to n times the logarithm of x. So all we did is if we have an exponent, we can bring it around here and multiply it times. We take the logarithm of x and then multiply it times n. That's useful in solving for unknowns that are in exponents. All right. That pretty much concludes our handout on math theory. I might like to take just a quick look at a couple of things in the worksheet just to clarify a couple of things there for you. On the first page on your worksheet, the first part is just simply things you ought to be able, the polar rectangular polar conversion. The next thing is how many degrees are in pi radians. The next thing is 360 degrees is equal to how many radians. Those are things you should already be able to do without any more assistance. The next thing is draw and label the phasor for a couple of sinusoidal expressions. The first one on my sheet I've got here is 69 sine of 377t plus 17 degrees. I might put brackets on there to clarify that we would have to do this. If I was going to solve this in my calculator now and get a value for this function as it's written, I would have to convert the 17 degrees to radians, then add it to the 377 times whatever time I was looking at, and then take the sine and be sure I'm in radians mode on my calculator. However, all I'm wanting you to do here is graph or show the phasor for that sine, that particular sine wave. The 17 degrees implies that the wave has been shifted. Normally we look at a waveform and we think that point is 0 degrees. In this particular case, it's been shifted 17 degrees to the left so that this is my 0 degree point. And the displacement or the shift is 17 degrees. Now, a phasor is a representation of a sinusoidal wave which can be either peak to peak, peak or RMS value for the magnitude of the vector, but the rotation or the number of degrees that the phasor is displaced from 0 represents any displacement in the phase shift of the signal. So this 17 degrees might look something like this, where this is 69 here. We'll just use peak. That would be 69 volts. And this is my phase angle displacement of 17 degrees. So that's what I'm looking for on those. The next one I have is 18 degrees. It's very close to that one. And the voltage value is 58, which is very close. Let's say I had one of, let's say I had 120 at, let's see, sine 377t plus, let's say, minus 30 degrees. Then that would be much longer. That'll represent the 120 degree, the 120 volts. And this would be my negative 30 degrees offset. And on my diagram over here, that would be a larger waveform. I don't want to go through mine now. I guess I just will. Something like that. Okay? Showing with 30 degrees shifted to the right. That's a negative phase shift. All right, that should take care of number 6 and number 7 as well. And I believe that's pretty much it. The rest of it you should be able to get from the theory handout with no problem. And of course the key is attached to your worksheet. And I hope that if you don't understand what's going on, that you will ask one of your instructors, and we'll be happy to help you.